constructed to get one of those pins and right on the board that records it.
Oh, yeah?
Oh, yeah. That's in the hearing class.
We have that board in one of the conference rooms. You could print out.
He had a weird pin.
You could print out what's on the board.
It would record what he said, so he just post that. But what it did is it like memorized your strokes on the whiteboard.
Cool.
So what it would do is it would just do a white screen, and that's how we get all his online classes.
That's pretty awesome.
Like, gave us time to do projects in class.
Damn.
Again, engineering, that's all of it.
All right, this is kind of related to one of my favorite types of questions, and you see this in the homework too. Nice, easy question. What's dy dx here? Now, can you rewrite that result in terms of y?
Yes.
Yep, write that result in terms of y. Okay, sure. Thank you. Well, I'll put a little purple. So I want a function of y here that makes, this is y, this is what dy dx is. Now I want you to have a function of y that makes this all true still. So we're kind of creating our own dE. Some of us are. Now tell me, I mean, if you had to tell me, you didn't know what derivatives were, and I said, well, how did this change? How did it change from this to this? Don't worry about the 3 yet, but from this to this. I don't know calculus. Explain to me how that changed. Not how did it change, but just what happened to it. What's one way to say what happened to it? Power decreased. Subtract 1 from the power. Now make it more basic. How do you do that? You take x cubed and you divide by x. Okay, so y is x cubed. If I divide by x, now it's x squared. And then the only thing missing is 3. Okay, right. Okay, so then, I mean, so if I had, let's write it like this. So by observation, now that you know this kind of idea, by observation, can you tell me at least one solution to that? There's a solution that is really, really stupid easy. Huh? 0, yes. So one answer is y equals 0. Thinking in this way. Now, so what's different between this statement and that statement? You can rewrite that, can't you? Yes. And then you can think in this way.
Y prime equals 2y over x?
Yes. Now that looks a lot more like this should, don't it? But now it's a 2. Correct? So that was a 3 because it was a third, went to a second. That's why it's divided by x. That's a 2, so it was a something and it went to a... So what did it start off as? Yeah, x squared. Right, because what would y prime be then? 2x, or 2x squared divided by x, or 2y divided by x. All right, let me stop there for a second. Now that is still unsatisfactory in a way, but at least it's starting to really kind of get a feel for what DEs on a really basic level are. They do introduce y, which is the function itself. And so to kind of start to get an idea of what they're trying to do, that you got to think, well, you know, what is it related to its own derivative? Right? And this is kind of related in the sense that the power goes down by 1. Okay, now I know it's some kind of polynomial in nature. Okay, now I can work with this. If I had y prime equals y, that's just e to the x. We talked about that before. And that's just a straight, direct equals. So there's only one thing that equals its own derivative, so that's nice. Okay, now, let me throw something else on top of this. That's not the only solution. And that's not a standalone solution. What? Well, let me just give it to you. Is that okay?
Yeah.
Of course it is. Because then it would be on both sides, and it would cancel, and it would still be true. Is everybody cool with that? So do you see how that's not really a separate solution? Because if I make C 0, then I capture that. Okay, I like it.
So would that be called a family of solutions?
Yes. Yeah, exactly. Beautiful. So that's a family of solutions. We did this by observation, but you could actually use the separable. Isn't this separable? You can integrate. You get a bunch of ln's. You have to raise it to an e and all this kind of bullshit. Eventually, you get here. I'm going to let you try it if you want to. It's not that bad. Okay, now, let me throw on top of this an initial condition. What if y of 1 was 1? And you see this in the homework. They give you a DE that they don't even really have to tell you because they give you the answer and then they say make the C so that this works. They don't say that actually. They say it in a very strange way. But that's how you translate it for yourself. In fact, the language they use, somebody's asked me, find a solution of the first order IVP consisting of this differential equation and the given initial condition. So how do you translate that? Find C so that the initial condition works. That's it. That's what it means. So here, how do I find C so that this works? I just plug it in. So I get 1 has to be C times 1 squared, so C has to be 1. So the answer is, the unique answer is y equals x squared. Right? Because we figured out C has to be 1. Is everybody with me? Now go back to the existence and uniqueness theorem. Why does that say that we should expect there to be a unique solution through 1, 1? What's f? What's f of xy? Who remembers? Y prime equals f of y and x. Right? F of xy. So this is f of xy. Is it continuous near this point? 1, 1. Yes. Where's the only place it has a problem? For x 0. Right? Y can be 0, but x can't be. Right? And what's the other thing I have to check? Well, they had an interesting conversation, but sure, the first and a half derivative of y, or more, the better, the partial of f with respect to y. That's it. Poor little f, it's its own function. And what's that? 2 over x. Right, the y just goes away because 2 over x is a constant coefficient of y in that case. All right, let me stop. And this is continuous. Is this continuous? Near 1, 1? Yes. So if I try to say this initial condition instead, all right, everybody's got this here, right? This is pretty nice and simple. If I try to say instead, okay, make this work. What does the existence and uniqueness theorem say? No, it just says, I have no idea. It didn't meet my requirements, so it could do anything. It could do what I say. It could do its own thing. I don't frickin' know. So let's try to figure out what the hell's going to happen. So what would happen here? What was the general solution was y equals cx squared? When x is 0, what is y? Does it depend on what c is? So how many answers do I get? Do I get a unique solution?
As many as you want.
I get a family of solutions. I don't get a unique solution. Very interesting. Now, that still doesn't fully explain why. And to be honest, I did have something that was related to this that was sort of an animation, and I found the link, and it's dead. It's not something I made. It's something I stole a long time ago, and it's dead. They were like, people linking to this thing. Let's take it out. But I do want to show you, if you want to, I can send this to you. I mean, I just want to show you. Here's part of the proof. Let me see, where is that? This part I might want to talk about. Let's see. Proof of the uniqueness part of the theorem. And it's a lot of weird shit. You should probably be able to slog through it if you really try to. But notice what pops up part of the way through the proof. This guy. And they use a capital F in this proof instead of a small f. Cool? Okay. Now that still is not fully answering the question. And to be honest, there's a lot more to it than this. This involves iterations to try to prove. So it involves like, I'm not going to, yeah, iterations. Blah, 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 blah. We're not going to get all the way through that. That's good. Go away. We're not going to worry about it. I do want to show you one little thing with this. If I put in 2y over x. Remember this guy? We looked at this guy last time? He constructs the direction field for me. Now, there are limitations to this poor little dude. So here's the initial condition 1, 1. And you notice it has resolution issues. And it's related to the fact it is a very strange thing, because it's 0 all along here, and it's also 0, not 0, but infinite along here. They should connect and make a full parabola, like we found out, right? Y equals x squared should be, well, it was up here earlier. Y equals x squared should be the answer, but it's got resolution issues. But when I try to put it, initial condition 0, 0, it just completely gives up. It's like, why does it do that? Because it's got infinite things trying to happen, so they could just make the whole thing green. Right? So instead it just goes, can't help you out there, buddy. Okay, maybe. Does that help a little bit with, again, to really show you full proof would take a little bit more math than I want to plunge us into. And this happens every now and again. Later, you'll take a class later. If anybody's really going down a real good math path, like a math major or something, you would eventually get to a class and they go, remember that thing? We're going to finally prove that. Remember that thing you did? You didn't even realize it, but you have to prove it, you know. Because you get up to a high enough level, then you can prove this shit that we used earlier, like right now. Maybe. Okay. So I wanted to get that out there. Any questions from homework? Any other questions from homework stuff? You guys are doing the homework right? I had somebody email me saying they weren't sure what the homework was, and that concerned me at this stage in the game. If you're not at least getting into 1-3, you're a little behind. Yeah. Okay. So I was hoping those 2 quizzes might put a light of fire into somebody's ass. Chapter 1 for Monday, so all of Chapter 1 could be on the quiz Monday. And then we'll see how far we get tonight. That's going to base what next Wednesday's quiz is going to be. It's going to at least 2-1, 2-2, if not parts of 2-3. We'll see. So nothing else from homework stuff? Okay. We left off. Let's see, where exactly? Oh yeah, we had just barely started talking about autonomous DEs. Just to remind you guys. So we talked about direction fields, right? And that's just little lineal elements showing the derivative at those points. So it's taking a step back from this equation and realizing that this function itself is the value of the derivative at those points. It's kind of a neat thing. It's not really a third dimension. It's an xy plane with slopes at each point. So it's not quite a z situation, truly. Okay. I try to give us a little bit of a feel for what we're about to do. So an autonomous DE, an autonomy, what does that word mean? Anybody know? If you're an autonomous state or an autonomous... self-governing. Exactly. So in this sense, it makes complete sense. I want the slope of y to be governed only by y. It governs itself. Poor little x gets no say. Right? So a real simple example would be like y squared minus y. So it's completely governed by itself. Its derivative is governed by itself. So that's why it makes sense to call it autonomous. It's awesome. Since there is no dependence on x, what would it look like? Not specifically, but what would be one feature of it you would expect if I plotted it? For every value of x, it looks the same up and down. So if I put in here Can we make a few predictions before I put this in here? Where is it going to have flat lineal elements? That would correspond to, what does flat correspond to? This equaling 0. So where would that happen? 0, 1, right? So y equals 0, y equals 1 are critical points. Okay, so let's double check. Let's see. So I put it in here. Y squared minus y. There we go. There's 1 and there's 0. And I think I might have done almost exactly that one last time. Can't remember. Okay, so, and do you see, as you look, any value of x you look at, if you look up and down, the picture is exactly the same as the one before it and the one after it. So to quickly, then that gives us a shortcut on how to do this. We just do it for one up and down cut, because it's going to repeat that forever in both directions, right? And what we call it is, we call it a phase portrait, just to be interesting. There's a whole series of reasons why we call it that. A phase portrait. What that really is just a slice capturing the whole idea of this DE's direction field. So what we do, I'm going to add some stuff on top of this, but I really want to make it clear what the phase portrait part is. The phase portrait part is this. Let me not even put that there. Nice vertical line to illustrate the slice we're taking. Put on here the critical points. At these critical points, what will the function look like? Along those critical points, what's the slope?
0.
So if I start at 0, if I have an initial condition that says like y of 3 equals 1, can it ever, is everybody with me? If my initial condition was y of 3 equals 1, what's the resultant solution curve look like? If I'm on the line, can I ever get off the line? No. The slope doesn't let me go anywhere. So then the solution would just be that constant. That's it. So sure enough, look, if y equals 1, that's an answer. Y equals 1 is an answer because that makes this side 0 and it makes this side 0. And y equals 0 does the same thing. So that's why the solution curve will be a constant, because that constant is an answer. Now if I live in between those, that's where things get interesting, right? Let me maybe give myself a little more room. There. If we live in between or outside of those, that's where things get more interesting. And this should feel very familiar. It's really doing something you did in 180 and taking it like this. What is the sign, SIGN, of the slope here for anything bigger than 1? You remember doing this kind of stuff? Yeah. So bigger than 1, this is going to be positive. So it's going to be going up. This is the official way to do this. And of course, in between 0 and 1, do you guys remember multiplicity and how that helps you with this kind of shit? Around its roots, it's going to change because they're both odd multiplicity. They're both 1. If you don't remember that, just plug a value in. 1/2, positive times negative. Going down. So over here, it's going to be going up. I like it. Negative 1 billion times negative 1 billion and 1 is positive. I just have to pick a number that's down there somewhere. Okay. That is the phase portrait. What I'm about to put on there are some additions to it related to other questions I ask. And the book asks too. Let me see if I have a... Yes, you work. Yeah. So along here, what do you think we're going to put along 1? Because that's going to be where... Yeah. And remember, hopefully it makes sense. Let me see if this really... Please tell me this makes sense. If you're born on the line, you can't get off that line. Either the 0 or the 1, right? If your initial value is on the line, you just can't get off of there. That's why the answer is that. Now turn that around. If you're not born on the line, can you get onto the line? No, because what's happening in the slope is you get really close. Smaller and smaller and smaller is asymptotic. It kind of makes sense. If you can't get off the line if you're on it, then you can't get on it if you're not on it. Right? If I could get on it, that means I should be able to work my way off of it too along that curve. So what we're going to do on top of this phase portrait, crap, when I move over here I can see how, it looks good here. And I'm like, oh shit. All right. That's that weird perspective that we have. All right, that's a little bit better, right? Okay. Go with me, you know what. What I'm going to put on top of the phase portrait in black ink is an extra thing. It's going to be, what does the solution look like in these three regions? So up here, the slope is positive. This is asymptotic. What do you think it's going to look like then? I mean, can it be coming towards it over here? Because then the slope would be negative. So obviously it's got to be like this. Now, this, I really want this, this line is not the y-axis because I don't know. It looks like this, but it could scoot anywhere along. Why can't it just move along like this? Why does it not matter? Why can it move along? Because it's repeated forever. X doesn't matter worth shit. So it depends on the initial condition. The initial condition. So if my initial condition was y of 0 is 2, then it might look something like this, right? It's got to go, y of 0 is 2. It's going to look like this. Cool. It's going to have that shape. It's going to go through there. But if y of 0 is 5, then it's going to have to look, well, I don't know. It's going to have to look like that. So where it crosses that y-axis depends on the initial condition. So if my initial condition is over here, it's going to be, meaning that point that somebody, so if they said, solve this with the initial condition, y of 4 is 5. Or, graph the solution, it would look like that. Can't like it. So it can translate left and right because it's not x dependent. Just like in Math 180. In Math 180, you solve something, you have to put the plus c, it can go up and down all day long, right? Because in Math 180, what do you start with? dy dx equals a function of frickin' x. So that's why it's able to move up and down as much as it wants to, because it doesn't depend on y. And then how do you tell? Initial condition tells me where the hell to put that sucker. Same way. Yes?
I'm a little confused on what makes the game an autonomous differential equation, because it just said there's no x in the function.
Totally. And again, I really want that to fully make, autonomy means you control yourself. dy dx is the derivative of y. It's controlled only by itself. X doesn't get a say. That's what makes it autonomous.
Are they always symmetrical?
How do you mean?
Like in this graph?
Oh, no. I mean, I could do a lot of weird shit here, right? And have the same, I could make this to the, 1/4 and make this to the 8th power, and yeah.
Then this would be symmetrical.
Yeah. I mean, and I can throw other parts into it. Yeah. Right? So this is a very, very basic one. I'd expect it to be kind of nice. And how do you mean symmetry, though? I mean, I got to be careful. It's always going to be repeated, always.
Yeah,
But do you mean like this kind of idea going on?
the upper and lower half of the stuff.
No, that won't always be. Yeah. In fact, all I have to do, if I did this, if I put a square here, like if it was y cubed minus y squared, that would make these the same sign. Right? So if I make this y cubed minus y squared, see what happens to the, see how it turned? Now it's even, now I'd argue that it's more symmetric. But now this is going up like that, this is going down like that. Does that make sense? Yes? Okay. Okay. All right, maybe. So what's going to happen in here? It's got to be asymptotic to both of these. Slope has got to be negative. So what's the only real way it could look like? It's got to start here. Yeah. Good old ceiling and a floor. And then finally, this guy is a lot like this guy. Got to be careful though. What's it going to look like down here? Yes. So it's got to always be increasing, and it's got to, I like it. Now let me ask you, let me see if I can push this a little bit. put this over here. What is this? Figure out what that is.
Second.
True. Now calculate it for the... I'm sorry, yeah. Calculate it for this given expression. This is what the first derivative is. Can you get the second derivative? This is also something you've done before, but maybe not with y's, but it's the same idea. It's like second derivative implicit stuff. This is not a partial, by the way, so I don't want anyone thinking the answer is 0. Y is a function of x. So, I mean, how do I do that then? What's the derivative of y squared with respect to x?
2y dx.
Yeah, 2y dy dx. Minus 1 dy dx. So I can take a dy dx out, right? So I get 2y minus 1 times y squared minus y, so times this. Right? You guys with me? Because it depends on the original derivative. That should also feel familiar. You've done that before, hopefully. With implicit differentiation, we have to do higher derivatives. So what are these all related to? What are all the critical points of these possibly related to? What are these related to? This is the second derivative. What are the critical points related to? Concavity, but the critical points of concavity, so they are related to possible inflection points. I like it. And sure enough, look at y equal 1/2. Look at y equal 1/2. Doesn't that kind of, now I sort of just did it, but I mean, it's because it kind of makes sense that right halfway in between should be where this sucker goes from concave down, in this case to concave up. Okay, I like it, I like it. So it at the same time that it feels very familiar, some of the stuff we're doing, it's also very alien. I understand this. They're both happening at the same time, but it's really nice to see this shit that you've done before just kind of showing up in the middle of this freaky-ass new stuff. And down here, so out here, there's another change of concavity here. So these are always the same concavity on either side, right? Because they don't have any critical points in the middle of them. They always have the same concavity, which makes sense. It's exactly what we expect. Okay, I like it. I like it. Okay. So, let's see if you guys are ready. Yes, you guys are ready for this. Oh, let me give you some terminology. You can never escape anything without some new terminology. This, unbelievably, is called a repeller. Oh my God. This is called a repeller. Get rid of this OR. I suck at spelling. Oh yeah, it is ER. What do you think this is called? A tractor. Because as I read it left to right, what does this thing seem like it's doing? Get away. This is like, come on down here. Right, so this is an attractor. I call this one stable. I call this one unstable. And then you can have one that's called semi-stable. If you had a down arrow and then another down arrow, that would be semi-stable. And it's not an attractor or a repeller. It's the one that's just a semi-stable. Does that? So if I had one that was like, here's a critical point, and it's down and down, this would be semi-stable, which a lot of us can relate to. What day is it? Yeah, maybe I'm stable. What did I eat? Okay, maybe I'm good. So, all right, I think I've got enough information to you so I can finally shut up and let you guys try this. So as always, with a little handout like this, you can work together. It's not a quiz or anything. I'm going to go over it in a little bit. Now's the time to feel free to make a lot of mistakes. Get them all out there so you can see why they're mistakes. This is not graded. Was that?
Where do you get the shirts?
This one was a gift. This is my other ones I get from Cafe Press. There's a website called Jinx.
You ever heard that one where it's like the graphic is lines draw the line?
I don't know if I've seen that one. It doesn't sound familiar.
Draw the line.
Yeah, algebra, we don't know what
I like it.
Yeah, so